In this video, we'll discuss about the Alain asbestos experiment on 1982 and its significance. Before to begin, there are several concepts we need to know in order to understand the experiment properly. In quantum entanglement, two particles are in a single entangled state such that measuring a property of one particle instantly determines that some property in another particle. It is more clear to understand with considering an experiment in which a particle with zero spin collapses into two particles, S1 and S2, with spin minus 1 over 2 and 1 over 2, and flies in opposite directions. In this case, the sum of each component, XYZ components, must be 0, which is the state of the original particle, according to the law of conservation of spin angular momentum. Since the second particle must have the opposite value of the first particle, measuring the first particle results in a definite state for the second particle, notwithstanding the fact that the two particles may be millions of kilometers apart and are not interacting with each other at the time. In 1935, when Albert Einstein, Boris Podolsky, and Nathan Rosen devised this paradox, they thought that this conclusion was so obviously false that the quantum mechanical theory on which it was based must be incomplete. They concluded that a correct theory would contain some hidden variable feature that would restore the determinism of classical physics. That is, the particles must be in some definite spin even before they are measured. In 1964, John Stuart Bell devised mathematical relationships, Bell's inequalities, that would be satisfied by a hidden variable theory in which measurement of one particle would not instantly determine the properties of the other particle. Contrary to its original intention, Bell's inequality has become very important in supporting quantum mechanics later on. Clauser and Friedman made the first experimental test of the Bell's inequalities in 1972 and showed results in accordance with quantum mechanics and not hidden variable theory. However, the Clauser-Friedman experiment did not test an assumption Bell made, which is that the measurement of a particle by one observer will not somehow affect the measurement of the other. For example, the Clauser-Friedman experiment used polarizers that were preset. What if the experimental setup somehow had selected only photons that did not behave in accordance with hidden variable theory? Aspect and his collaborators in the early 1980s performed a series of experiments designed to answer such questions. The most spectacular experiment was a modified version of the Clauser-Friedman experiment. A pair of photons with opposite polarizations was emitted from a heated calcium source. Each of the photons traveled toward the polarizer. The polarizers were 12 meters, 40 feet apart. The time for light and thus any conceivable signal to travel between the two polarizers was 40 nanoseconds. The experiment had switches that would send the photons between two pairs of polarizers every 10 nanoseconds. Thus, each polarizer was independent of the other because no signal could travel between the two. Aspe, Dalibort, and Roger measured a quantity S, as S equals 0.101 plus or minus 0.02, which was not in accordance with hidden variable theory, but was in accordance with the quantum mechanical value of 0.112. Aspe's experiment showed the invalidity of Bell's inequality, which was designed to support EPR paradox, which Einstein, Podolsky, and Rosen proposed, arguing that quantum mechanics is incomplete physical theory. Moreover, he proved non-locality of quantum, such that the influence received by one transcends space and is immediately transmitted to the other along quantum entangled particle pair. Aspe's experiment not only demonstrated the validity of quantum mechanics experimentally, but also laid the foundation for quantum computer, quantum network, and quantum cryptographic communication research. He was awarded the Nobel Prize in Physics 2022 in recognition of his contributions. Thank you.